We have repeatedly said that the ocean water density is a nonlinear polynomial or high order polynomial of temperature and salinity, which creates some unique properties in terms of ocean water density and ocean water mixing. This kind of TS diagram, temperature salinity diagram, is very common for physical oceanography, hydrography, observational oceanography, ship-based measurements, mooring-based measurements, and so on and so forth. And it shows this nonlinearity here. You can see that the constant density lines are not linear lines. So if you look at density of 1027 kilograms per meter cube, then you have Antarctic intermediate water here going along this line here, and you have, that's this water here, Antarctic bottom water here, North Atlantic deep water here, and obviously as temperature warms, density decreases, and as salinity increases, density increases. So inversely related to temperature and directly proportional to salinity. But something more amazing happens. If you take two water masses A and B on this density line 1023 and mix them, combined density of average temperature and average salinity resulting from the two water masses, which are giving you 1023 at different combinations of temperature and salinity, remains almost the same. Whereas if you go to another density line here at 1029, you see that if you mix C, which is also of the same density, with D, which is of the same density but warmer temperature and higher salinity, here colder temperature and lower salinity, then you end up with a third density CD, because the average temperature and average salinity of C and D give you a third density because of this nonlinearity. This process of forming a third density obviously means same density water can come together and get heavier and sink, right? So this is going in this CD is higher than 1029 and is towards 1030, which means same densities came together and water sinks because it's heavier water now. Okay, so this kind of nonlinearity is very common, and in fact you can find buoyancy fluxes of cabling in the ocean. Southern Ocean has a dominant band of cabling, and so does the North Atlantic, where such water mass mixing happens. So if you look at also in terms of, let's say you draw a line at constant salinity and look at 5-degree temperature change here and see how much the density changes versus a 5-degree change here and see how much the density changes, then the density change at the warm water can be relatively small compared to cold water by an order of magnitude almost. So the dependence of density on temperature is related to how warm or how cold it is. So that all these kinds of nonlinearities happen here. So temperature salinity diagram based on the equation of state giving seawater density in kilogram per meter cube for a wide range of temperatures from 0 to 30 degrees centigrade and salinities 33 to 38 gram per kilogram, or practical salinity unit that we talked about before, for pressure at the mean sea level. So even though we mostly assume ocean water is incompressible, there is a pressure dependence, especially the salinity dependence coefficient and temperature coefficient for density are not independent of pressure. The heavy black features illustrate cabling, or the process of two water masses with the same density mixing to create a water mass of greater density. Two hydrographic profiles are shown from the South Atlantic. So you can see there is one at 20 south and there is one at 1.5 degrees south. So in the subtropical gyre and in the deep tropical Atlantic, which we will see in a minute somewhere. Okay, sorry about that. Okay, one at 25 degree west, 20 south, and one at 25 degree west, 1.5 degree south. So you're going around along the same longitude. Temperature and salinity values plotted are roughly every 10-meter depth. Water masses labeled include North Atlantic deep water, Antarctic intermediate water, and Antarctic bottom water. You can see the density of the Antarctic bottom water at 1028 is about the heaviest we have in the oceans. Okay, we can define now move towards defining buoyancy. So if you think about this example Chris uses in his book, is that there is a person, let's say, hiking in the jungle, and he sees a lightning strike happening over there, and then he hears the thunder arrive to where he is with the time lag, let's say delta t. So delta x or delta t is the speed with which the sound travels. So he has to figure out how close the lightning is actually occurring compared to where he is. So he has to determine the distance delta x. So if he knows the speed of sound and the time difference from the lightning strike to the sound arriving to him, then he can approximate that distance. And Chris argues that there could be uncertainties in this because the hiker is scared and not measuring time accurately, or didn't know exactly where and when the lightning struck, and so on and so forth. So we use that kind of partial differential equation to estimate various quantities, as we will see. So the density, then flux of density, can be written as a function of thermal expansion coefficient and function of temperature, plus a salinity expansion or salinity dependence coefficient times the salinity flux. So density flux is a function of temperature flux, and salinity flux, which is related to alpha, which is a indicator of how density is dependent on temperature, and beta, which is an indication of how density is dependent on salinity. Of course, we are making a linear approximation here. After saying that the temperature and salinity produce a very non-linear relation for density, we are immediately coming and saying a density flux can be estimated as a linear function of temperature flux and salinity flux. So near the surface, that's okay. Warmer temperatures, you can assume that this relation is almost linear, whereas at some other ranges obviously the non-linearity is high. Okay, keeping that in mind, you can write the temperature flux as net heat flux that we looked at divided by the heat capacity rho Cp, and salinity flux we had written as salinity times E minus P, where it's evaporation minus precipitation. So in that case, the density flux becomes d rho dt alpha times Q net over rho Cp plus d rho ds times S times E minus P, the salinity flux. Okay, so we have moved from salinity budget and heat budget to now doing sort of density flux. So this can be written as a buoyancy flux, because buoyancy is a concept of the relative density in the vertical, considering the water is stratified. Where you are is determined by the water density of the water below you and density of the water above you. So that's related to gravity. So the buoyancy flux then, in a simple way, is written as minus g, which is the gravitational pulse, because if you are lighter you will go up, if you're heavier you will come down. So the negative sign takes care of that, times the density flux we just wrote, F rho divided by rho 0, which is kind of the mean background state. So your buoyancy is going to be how light or heavy you are compared to the background state. If you are at a position and you are heavier than the background density that is usually found, let's say long-term climatological density, then you will, if you are lighter, you will tend to move up because buoyancy is positive. If you're heavier, you're going to sink into the ocean deeper, so that's going to be usually negative buoyancy means lighter, positive buoyancy means heavier. Okay, so nonetheless, you get the idea. Okay, so Ray Schmidt computed these things based on earlier calculations and data. So these are maps of total annual average density flux in kilogram per meter squared per second. So it's density per unit area and time per second. Okay, so this is the thermal density. This is the thermal density. So I screwed this up somehow. Nonetheless, so this is the net density flux. So where we are only looking at the North Atlantic, so where the Gulf Stream is bringing very warm water, and heat loss is happening, evaporation is happening, and salinity is increasing. So there is a positive salinity flux here, and temperature is alpha ft is positive, and beta dsdt is positive. So if this is positive, that means density is going to get lighter. Heat loss, so you have to just make sure you got the right angle. So Q net is positive, rho Cp is positive, so Ft is positive, but this means the water is getting lighter, whereas here salinity is getting increased, which means density is getting increased. So in the net you have net density flux. So there is water getting heavier in these regions, which makes sense because this is the region where we are forming the North Atlantic deep water. Okay, so just make sure you get the sense of the temperature flux, salinity flux, and the net density flux in kilograms per meter squared per second. Okay, so we'll come back and look at what this means in terms of thermohaline circulation. So we were looking at 25 west at 20 south and 1.5 south before. So those are the two spots. We'll come back and look at how the meridional transport of density happens along these two transects in the next podcast. Okay, so I hope it's clear and I didn't fumble it too much. Okay, see you in the next podcast.